Now we're going to talk about decay on our model. And in this particular example, we're talking about carbon-14, which is something that you might be familiar with as far as carbon dating is concerned. So that's the example we're going to look at here. It says the half-life of carbon-14 is 5,715 years, meaning that after that amount of time, a given amount of the substance will have decayed to half of the original amount, which is important for us. So the first thing I want to do is find the exponential decay model for carbon-14. In other words, we have to find K first and then put that into the model we're looking for. So let's kind of see how we're going to start here. We know that we have the growth and decay model A equals A naught e to the k t. We also know that at time 5715, the amount of carbon is half of the original amount. So I'm going to write that as A naught divided by 2. So remember that this A is for any time t. So when our time, let me write this a little different, when our time is 5,715 years, the amount of carbon we have left is half of what the original amount was. So A naught stays in there, e to the 5,715 k. All right, now what do we want to do? Well, I'm going to shift this over for just a second so you can see some of my algebra that I have in here. And what I want to do is I'm trying to isolate e and the variable k, right? So I've got to divide both sides by A naught. I already have a fraction over here, so I'm going to do this a little different. Rather than dividing by A naught, I can multiply by the reciprocal. If I divide by A naught, that's the same as multiplying by 1 over A, because this A naught cancels with that A naught. And then I can multiply the other side by A naught. That doesn't give me that kind of it allows me to not have a compound fraction like a division over a division, and instead it just whips me over here so I can cancel these fractions diagonally. So it's doing the same thing. When I divide, I am actually multiplying by a reciprocal. So I am left with then 1/2 on the left equals e to the 5,715k, and I can now take the natural log of both sides. So the natural log of both sides. Remember, when I take the natural log of e, I just get the exponent. 5,715k is now equal to the natural log of 1/2. Divide both sides by 5715, and I get k is equal to the natural log of 1/2 divided by 5715. Now I've done this in the calculator already for you a couple of times, so I'm just going to show you that when you do that, you should get -0.000121, and that is the K, or the constant, for carbon-14. So what's the model going to look like then? The model, let's put it back over here, the model is going to be A equals my original amount, A naught, e to the -0.1230121 for any time t. And that's the model representing that carbon-14. The next part of this question says, okay, well, in 1947, the Dead Sea Scrolls contained 76% of the original carbon-14. Estimate the age of the scrolls. So what we're looking for is how old were the Dead Sea Scrolls in 1947? Well, using my formula or my model that I have right here, it says that in 1947, 76% of the original carbon was there. So if we just take 0.76 times my original amount equal to A naught e to the -0.123121 and solve for t, because it's the 76% of the original amount and we're trying to solve how old, what was the date of that this was occurring. So this algebra is just a little bit easier because I am just going to simply divide both sides this time by a naught. Those a's cancel, leaving me with 0.76 equals e to that number. I can now take the natural log again of both sides. And when I do, I get negative 0.123121 times t is equal to the natural log of 0.76. Divide both sides by that number. T is equal to the natural log 0.76 divided by 0.000121. And when I put this into the calculator and I round it to the nearest year, I find that it's 2268. So 2,268 years old when they found them in 1947. And they were able to find out that age of them because of the amount of carbon that was left in the actual scrolls.